In the summer of 1967, on the outskirts of Cambridge, a young graduate student named Jocelyn Bell was engaged in what might have seemed, at first glance, like a mundane task. With practiced hands, she scrolled through endless paper chart recordings, each marked by the steady, jagged line of cosmic radio noise. For months, Bell had been immersed in the construction and operation of a vast new radio telescope, the Cambridge Dipole Array. This remarkable, sprawling structure stretched across the fields, designed not for the unknown, but to probe the enigmatic signals known as quasars. Yet, as so often happens in science, the search for one mystery led to the discovery of another, entirely unanticipated. The telescope's design, born of ingenuity and determination, was both ambitious and practical. Its purpose was to study distant, energetic sources, but as Bell sifted through the relentless tide of data, she noticed something that simply did not fit. Amid the usual cosmic scruff, as she called it, a faint, odd squiggle caught her eye. A signal so subtle it was, by her own estimation, just 1 part in 10 million above the background noise. It was August 1967, and this anomaly would soon shake the foundations of astrophysics. At first, Bell could not be sure what she had found. The signal was fleeting and faint, easy to overlook or dismiss as terrestrial interference. But she was methodical. She marked the time and place, then returned, night after night, shoulder to shoulder with the whirring pen of the chart recorder, searching for a pattern. Before long, she discovered this was no random blip. Instead, it was a train of sharp pulses, each separated by a regular interval of 1.33 seconds. The precision was uncanny, like the ticking of an unseen cosmic clock. Her supervisor, Anthony Hewish, soon joined the investigation. Together, they set out to rule out every conceivable earthly cause: radio interference, equipment malfunction, even pranksters. Nothing fit. The signal remained unwavering in its regularity, indifferent to the comings and goings of the day. As weeks passed, their caution turned to excitement and then, inevitably, to speculation. The regularity of the pulses was so extraordinary, so unlike anything seen before, that the possibility of an artificial source could not be ignored. Half in jest, half in earnest, the team dubbed the signal LGM-1, Little Green Men 1. But the universe, as it so often does, had a different story to tell. When Bell discovered a second pulsing source in a completely different part of the sky, the odds of an extraterrestrial civilization behind the signals plummeted. Soon, a third and a fourth would be found, all within a span of 2 months. The evidence was mounting. This was no artifact of human technology, nor a signal from distant intelligence. This was a new class of cosmic phenomenon, one that demanded explanation. News of the discovery traveled quickly, and by February 1968, the findings were published in the prestigious journal Nature. The paper described the detection of regular radio pulses, the careful elimination of all known terrestrial and celestial sources, and the tantalizing possibility that these signals originated from a previously unimagined type of star. The scientific community was abuzz. Early hypotheses ranged from white dwarfs, dense, burnt-out stellar remnants, to neutron stars, objects theorized but never before observed. It was the neutron star hypothesis that would soon prevail. In the wake of the discovery, physicists such as Thomas Gold proposed that these pulses were produced by rapidly spinning neutron stars, the collapsed cores of massive stars left behind after supernova explosions. The extraordinary density and magnetic fields of such objects, combined with their rapid rotation, could, in theory, produce beams of radio waves that swept across space like the beam of a lighthouse. Each time the beam pointed toward Earth, radio telescopes would register a pulse. Thus, the pulsar, short for pulsating star, entered the astronomical lexicon. The first of these newfound objects received the designation PSRB 1919+21, reflecting its position in the sky. Its period of 1.3373 seconds was measured with remarkable precision. The nickname LGM-1 lingered in the public imagination, a testament to the sense of wonder and the whirlwind of speculation that had accompanied the discovery. But the reality proved, as it often does, to be even more extraordinary than fiction. These pulses were not messages from distant civilizations, but instead the dying echoes of stars, spinning with unimaginable speed and power. Jocelyn Bell's role in this discovery cannot be overstated. She had not only built much of the telescope by hand, connecting cables and hammering stakes into the ground, but had also shown remarkable perseverance and insight in identifying and investigating the anomalous signal. Her careful, systematic approach, scrutinizing miles of paper charts, sifting through noise, and refusing to dismiss the scruff, was crucial. It was a vivid reminder that scientific breakthroughs often depend not just on advanced technology or grand theories, but on the keen eye and dogged persistence of a single observer. The cultural impact of the discovery was swift and profound. Pulsars were soon recognized as cosmic lighthouses, their regular pulses serving as some of the most precise clocks in the universe. Their existence provided the first direct evidence for neutron stars, objects whose very presence had been the subject of speculation since the 1930s. The discovery also had far-reaching implications for our understanding of stellar evolution, the life cycles of stars, and even general relativity, as pulsars became laboratories for testing the laws of physics under extreme conditions. Within a year of Bell's initial detection, dozens of pulsars had been found. The Cambridge team's discovery unleashed a flurry of research as astronomers around the world turned their radio telescopes skyward in search of these new cosmic beacons. The original detection, once a faint irregularity on a strip chart, had opened a new window onto the universe. Yet, the story of the discovery is not only one of scientific triumph, it is also a story of recognition and controversy. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish, Bell's supervisor, and Martin Ryle for their pioneering work in radio astronomy and the discovery of pulsars. Jocelyn Bell, whose painstaking labor and insight had been central to the breakthrough, was notably omitted. This omission sparked debate within the scientific community and beyond, raising questions about the recognition of contributions and the role of women in science. Over time, Bell's achievement has been widely celebrated, and she has become a powerful advocate for diversity and inclusion in science, using her platform to champion underrepresented voices. The discovery of pulsars has echoed beyond the realm of astronomy, touching culture and the arts. The distinctive pattern of the first pulsar signal, that series of precisely spaced pulses, has even appeared on the cover of a Joy Division album, a subtle tribute to the intersection of science and creativity. From the first faint scruff on a paper chart to the recognition of pulsars as a new class of astronomical objects, the journey was marked by curiosity, perseverance, and the courage to pursue the unknown. Jocelyn Bell Burnell's discovery in 1967 did not just reveal a new kind of star, it transformed our understanding of the universe and our place within it. The story of pulsars is a reminder that the cosmos still holds secrets, waiting for those patient and persistent enough to listen. Imagine a star, vast and luminous, reaching the end of its life in a spectacular explosion. This is a supernova, a cosmic event so violent it can briefly outshine an entire galaxy. Yet the true marvel often comes after the light has faded, as the core of that star collapses into a remnant so small and dense that it defies ordinary comprehension. From the ashes of this cataclysm, a neutron star is born. For some of these remnants, an even more remarkable fate awaits. They become pulsars, among the most extraordinary objects in the universe. To truly understand pulsars, we must begin with their origins. When a massive star, typically between about 8 and 20 times the mass of our Sun, exhausts its nuclear fuel, its core collapses under gravity's relentless pull. The outer layers are cast off in the supernova, while the core compresses to a sphere roughly 10 kilometers across, about the size of a city, yet with a mass greater than the Sun's. This is a neutron star, a cosmic object so dense that a teaspoonful of its material would outweigh Mount Everest. The first clear connection between neutron stars and supernovae was established not through theory, but by observation, when astronomers found pulsars nestled within the remnants of well-known supernova explosions, such as those in the Crab and Vela nebulae. These discoveries revealed that neutron stars could persist at the heart of supernova remnants, spinning rapidly and emitting regular bursts of radio waves detectable from Earth. What then sets a pulsar apart from other neutron stars? The answer lies in their extraordinary physical properties and the mechanisms that drive their signature pulses. A pulsar is a rotating neutron star with an intense magnetic field, among the most powerful known in the universe, reaching strengths up to 1 trillion times greater than Earth's. This magnetic field is not aligned with the star's spin axis. Instead, it is tilted, and as the neutron star rotates, its magnetic poles sweep through space like the beams of a cosmic lighthouse. The defining feature of a pulsar is its astonishing rotation. When the progenitor star collapses, its core contracts from something the size of our Sun to a sphere just tens of kilometers across. By the laws of physics, this dramatic shrinkage spins up the star much like an ice skater accelerates by pulling in their arms, leading to initial rotation periods as short as a few milliseconds. The pulse period of a pulsar, the time between successive bursts observed from Earth, is directly tied to this rotation rate. Some pulsars spin hundreds of times per second, while others are more leisurely, with periods stretching to several seconds. Regardless of speed, the regularity of these pulses is astonishing, rivaling the precision of atomic clocks. The true spectacle, however, lies in the interplay between the pulsar's rotation and its magnetic field. Because the star's magnetic field is tilted relative to its spin axis, each rotation causes the magnetic poles to sweep around in space. Surrounding the neutron star is a region known as the magnetosphere, filled with plasma-charged particles torn from the star's surface by intense electric fields generated as the magnetic field whirls through space. These fields are so powerful that they can rip electrons from the surface, hurling them outward at nearly the speed of light. It is at the magnetic poles that the magic happens. Here, the combination of strong electric and magnetic fields accelerates charged particles along the field lines, creating beams of electromagnetic radiation. These beams are not emitted in all directions. Instead, they are focused into narrow cones that emerge from each magnetic pole. If Earth happens to lie in the path of one of these sweeping beams, we detect a pulse of radiation each time the beam crosses our view. This is the lighthouse effect that gives pulsars their name. The radio pulses we observe are the direct result of this geometry. We see only those pulsars whose beams happen to sweep past Earth, much as a distant ship at sea glimpses a lighthouse only when its beacon turns their way. Delving into the physics of these radio pulses, the mechanisms become even more fascinating. As the neutron star spins, the movement of its strong magnetic field through space induces powerful electric fields. These fields accelerate charged particles, primarily electrons and positrons, away from the star's surface, especially near the magnetic poles. The acceleration is so extreme that these particles emit gamma rays, which in turn can interact with the magnetic field to create even more particle pairs, a process known as pair production. The result is a seething plasma of electrons and positrons pouring out along the magnetic field lines. Within the pulsar's magnetosphere, especially near the poles, the conditions are ripe for coherent emission processes. One leading idea is that plasma instabilities, turbulent interactions among the streaming charged particles, give rise to powerful bursts of radio waves. The emission is not random, but organized, often in the form of coherent maser emission, where waves are amplified as particles move in lockstep. The exact details of this process remain an area of active research, but what is clear is that the pulsar's magnetic field and rotation combine to create an environment where ordinary physics gives way to the extraordinary. The structure of the pulsar magnetosphere plays a critical role in shaping the radio emission we detect. Close to the star, the magnetic field dominates, guiding particles along tightly wound paths. At greater distances, a boundary forms, the so-called light cylinder, beyond which the co-rotation speed would exceed the speed of light, an impossibility. It is within this region, inside the light cylinder, that the most intense emission occurs. The polar caps areas near the magnetic poles become hotspots for particle acceleration and radio emission, with plasma continually being ripped from the surface and funneled outward. Models of pulsar emission, such as the polar gap and space-charge limited flow scenarios, attempt to describe how particles are extracted and accelerated. In the polar gap model, a region near the magnetic pole is devoid of charges, allowing a strong electric field to build up and accelerate particles into the magnetosphere. In the space-charge limited flow model, the flow of charged particles is limited by the ability of the star's surface to supply them, resulting in a steady but powerful outflow. Both models agree that the interplay between rotation, magnetic field, and electric field is crucial in generating the beams that make pulsars visible across the cosmos. The observed properties of pulsars are as remarkable as their origins. Their magnetic fields, typically in the range of 100 million to several trillion Gauss, are immense by any standard. For comparison, Earth's magnetic field is about 1/2 a Gauss. The density of a neutron star is equally staggering, so great that atomic nuclei are crushed together, forming a sea of neutrons. This extreme state of matter, found nowhere else in the universe, challenges our understanding of physics and provides a natural laboratory for exploring the limits of known laws. Pulsars are not static objects. Over time, their rotation slows as energy is lost through the emission of electromagnetic radiation and the acceleration of particles. This gradual spin down is a key clue to their evolution. In young pulsars, the rotation is rapid and the magnetic field is strong, leading to intense emission. As they age, the rotation slows and the emission weakens, eventually fading from view as the pulsar crosses the so-called death line, where the conditions are no longer sufficient to produce observable pulses. Yet, even as they fade, pulsars leave a lasting legacy. Their regular pulses serve as cosmic beacons, allowing astronomers to probe the structure of our galaxy and test the laws of physics under conditions impossible to replicate on Earth. The connection between pulsars and supernova remnants, observed so clearly in the Crab and Vela nebulae, has deepened our understanding of the life and death of stars. And the study of their emission mechanisms, how beams of radio waves are generated, shaped, and emitted, continues to push the boundaries of astrophysics. In the end, pulsars stand as monuments to both destruction and creation. Born from the death throes of massive stars, they embody the extremes of nature: immense density, dizzying rotation, and magnetic fields of almost unimaginable strength. Their beams sweep the cosmos, silent except for the tick-tock of their pulses, revealing secrets about the universe with every revolution. As we listen, each pulse brings us closer to understanding the profound mechanics at play in the hearts of stars and the breathtaking ingenuity of nature itself. Pulsars, those rapidly spinning remnants of stellar deaths, come in a fascinating variety, each revealing new mysteries about the universe. Among them, millisecond pulsars and magnetars stand out for their extreme properties and the unique insights they offer into the cosmos. To truly appreciate their significance, we must consider not only what they are, but also how they are distributed throughout the galaxy, what distinguishes them from one another, and, most importantly, how they serve as natural laboratories for the most extreme physics imaginable. A pulsar's defining features, its spin rate and magnetic field, form the basis for their classification. Millisecond pulsars, as their name suggests, are champions of speed, spinning hundreds of times per second. Their rotational periods can be as short as 1/1000th of a second. This incredible pace far exceeds that of ordinary pulsars, which typically rotate once every second or every few seconds. What truly sets millisecond pulsars apart, however, is their formation history. These objects are believed to have been spun up by accreting matter from a companion star, a process that gradually increases their rotation rate over millions or even billions of years. The result is a neutron star that has been recycled, spun up to dizzying speeds, and left with a magnetic field that is relatively weak compared to their slower cousins. Weak here still means 1,000,000,000,000 times the strength of Earth's field, but it is low by pulsar standards. Magnetars, in contrast, are the magnetic giants of the neutron star family. Their magnetic fields are, by some estimates, 1,000 times stronger than those of typical pulsars, reaching values up to a quadrillion Gauss. This is so extreme that it distorts the very vacuum of space around them. Magnetars tend to spin much more slowly than millisecond pulsars, with rotation periods measured in seconds rather than milliseconds. Their intense fields are thought to originate from dynamo effects during the earliest moments after the neutron star's birth, though the exact origins remain an active area of research. The powerful magnetic fields of magnetars give rise to violent phenomena, including energetic X-ray and gamma-ray flares, making them some of the most dramatic objects in astrophysics. The Milky Way is home to a rich population of pulsars, but their distribution is far from uniform. Most are concentrated along the plane of the galaxy, tracing the disk and spiral arms where stars are born and die. Sophisticated models of pulsar populations, based on data from large-scale surveys, suggest that there are thousands of active, potentially detectable pulsars in our galaxy, though only a fraction have been observed so far. The birth rate of pulsars is closely tied to the rate of supernovae, with new pulsars born roughly every few decades within the Milky Way. Surveys indicate that the local surface density of pulsars, how many are found per square kiloparsec, varies with distance from the galactic center, peaking in the inner regions and tapering off toward the outskirts. The search for pulsars is ongoing, and advances in telescope technology have led to a steady stream of new discoveries. Sensitive surveys, such as those conducted with China's 500-meter aperture spherical telescope, have uncovered dozens of previously unknown pulsars by combing through vast archives of radio data. In one recent instance, 19 new pulsars were identified from a single dataset, demonstrating the value of both new observations and reanalysis of existing material. These discoveries not only expand the catalog of known pulsars, but also refine our understanding of their distribution throughout the Milky Way. The galactic center, in particular, is an area of intense interest. Despite challenging observational conditions, dense clouds of gas and dust obscure radio waves, astronomers have managed to identify candidates for both ordinary and millisecond pulsars near Sagittarius, a star, the supermassive black hole at the heart of our galaxy. The discovery of a possible millisecond pulsar so close to this gravitational giant offers tantalizing opportunities to probe both the pulsar's properties and the extreme environment surrounding the black hole. Pulsars are far more than celestial curiosities. In a very real sense, they are laboratories for physics that cannot be replicated on Earth. The conditions inside a neutron star push the limits of our understanding of matter and energy. Densities reach values found nowhere else. Atomic nuclei are crushed together so tightly that new forms of matter may emerge. In these depths, the behavior of hadrons, particles like protons and neutrons, can be studied through astrophysical observation. Pulsars thus serve as natural laboratories for nuclear and particle physics, offering clues about the strong force and the equation of state that governs matter at ultra-high densities. Beyond their interiors, pulsars are also testbeds for gravity and fundamental physics. Their rapid, regular pulses act as cosmic clocks, so precise that deviations as small as a few billionths of a second can be detected from Earth. This precision allows astronomers to use pulsars to test Einstein's theory of general relativity in strong gravity regimes, far beyond what is possible with solar system experiments. In particular, pulsars orbiting close to massive objects such as other neutron stars or even black holes provide unique opportunities to study the warping of spacetime, the emission of gravitational waves, and the possible existence of exotic phenomena like frame dragging. One of the most ambitious projects taking advantage of the regularity of pulsar signals is the hunt for gravitational waves. While ground-based detectors such as LIGO and Virgo are designed to catch fleeting ripples from colliding stellar mass black holes or neutron stars, pulsar timing arrays take a different approach. They monitor the arrival times of pulses from an ensemble of millisecond pulsars scattered across the sky. The idea is that passing gravitational waves, such as those generated by orbiting pairs of supermassive black holes, will subtly shift the timing of these pulses in a correlated way. By comparing the signals from many pulsars, astronomers can search for the faint, ultra-low-frequency gravitational waves that would otherwise go undetected. This approach has already yielded tantalizing hints of a cosmic heartbeat in the timing of certain pulsars, suggesting that the very fabric of spacetime may be vibrating on timescales of years or decades. Millisecond pulsars are especially valuable for such work thanks to their remarkable stability. Their pulses are so regular that they rival the best atomic clocks on Earth. And timing measurements can be used not only to search for gravitational waves but also to measure the masses of companion stars, probe the structure of the Milky Way, and even look for subtle effects from dark matter or other exotic physics. The crab pulsar, meanwhile, remains an object of intense study for its unique emission properties, including unusual spectral features that provide clues to the physics of neutron stars and supernova remnants. Pulsar signals do not travel through empty space. Along the way, they interact with the interstellar medium clouds of gas, dust, and magnetic fields scattered between the stars. This interaction can cause scintillation, a twinkling effect similar to the way stars appear to shimmer in the night sky. By analyzing how pulsar signals fluctuate as they reach Earth, astronomers can infer properties of the intervening material, map the distribution of plasma in the galaxy, and correct for distortions in pulsar timing. These corrections are essential for the precise measurements needed in gravitational wave searches and tests of fundamental physics. The study of pulsars has even illuminated the distant past of the universe. Observations of their signals and the way those signals interact with interstellar space can provide information about conditions in the early universe, including hints of possible phase transitions that occurred when the cosmos was still young. In sum, pulsars are distributed throughout the Milky Way, with concentrations in the plane and spiral arms, and a particularly intriguing population near the galactic center. Their diversity, ranging from the ultra-fast millisecond pulsars to the magnetic titans known as magnetars, reflects the variety of astrophysical processes that create and shape them. Each type of pulsar offers a unique window into extreme physics, from the behavior of matter at nuclear densities to the bending of space-time itself. Through their regular pulses, pulsars connect us to some of the most profound questions in science, serving as cosmic clocks, laboratories, and messengers from the most violent and enigmatic corners of the universe. With every new discovery, astronomers draw closer to unraveling the secrets these remarkable objects hold, and the universe reveals itself to be even stranger and more wonderful than we ever imagined. The story of pulsars is no longer limited to the discovery of mysterious cosmic beacons or the exploration of their extreme physics. Today, pulsars are central to modern astrophysics, driving technological innovation and transforming how humanity explores, measures, and understands the universe. This is a story of ingenuity, of ever larger telescopes, ever faster computers, and the relentless pursuit of precision. Over the past decade, pulsar research has advanced rapidly, fueled by a new generation of observatories and breakthroughs in instrumentation. The 500-meter Aperture Spherical Telescope, or FAST, in China, stands as a striking example. Not only is it among the largest radio telescopes ever built, but its innovative design and data processing pipelines have enabled astronomers to discover pulsars that would have eluded older instruments. The first pulsar found by FAST served as a proving ground for these new data acquisition and processing systems, heralding a future where discoveries are limited only by our ability to sift through vast amounts of cosmic signals. Pulsar astronomy now extends beyond radio wavelengths. When astronomers detected their first pulsar using the Atacama Large Millimeter Submillimeter Array, or ALMA, it marked a significant leap forward. ALMA's advanced technology, designed to probe the coldest and dustiest regions of space, now enhances our understanding of pulsars as well. Capturing pulsar signals across new frequency bands has opened a fresh window on the physics of these stellar remnants, revealing details invisible to traditional radio telescopes. Yet the true revolution is unfolding behind the scenes, within the intricate network of hardware and software that underpins pulsar observation. The Green Bank telescope, for instance, has led the way in developing ultra-wideband receivers, devices capable of sweeping up a vast range of the radio spectrum in a single observation. These receivers, combined with high-precision digital backends and sophisticated timing software, allow astronomers to capture and analyze pulsar signals with unprecedented accuracy. This leap in timing precision is far more than a technical achievement. It leads directly to new science, from probing the interiors of neutron stars to searching for the faint tremors of gravitational waves rippling through space-time. Institutions like the Max Planck Institute for Radio Astronomy in Bonn are hubs for developing specialized pulsar instrumentation. These include ultra-fast digitizers, high-throughput data processors, and ingenious algorithms that can identify a hidden pulsar amid cosmic noise. The challenge is immense. For every real pulsar, there are countless false alarms, bursts of interference, electronic hum, or distant lightning. Success requires not only sensitive equipment, but also the computational power to filter, classify, and confirm new candidates, a task increasingly entrusted to machine learning and artificial intelligence. Looking ahead, the Square Kilometer Array Observatory, known as the SKA, promises to transform the field once again. When operational, the SKA will offer sensitivity and frequency coverage on a scale never before attempted. Scientists anticipate it could double the number of known pulsars, revealing populations scattered throughout the Milky Way and perhaps even in neighboring galaxies. With so many new discoveries, the SKA will help researchers tackle questions ranging from the nature of gravity and the structure of the galactic magnetic field to the formation and evolution of neutron stars themselves. But pulsars are more than objects of curiosity or laboratories for extreme physics. Their regular, predictable pulses have made them practical tools, cosmic clocks and lighthouses that can be harnessed for navigation, timekeeping, and even communication. Millisecond pulsars in particular stand out as some of the most stable natural clocks known, their rhythms rivaling and sometimes surpassing the best atomic clocks on Earth. This reliability has led to their use in high-precision timekeeping, where pulsar signals help steer and calibrate terrestrial clocks, correct drift in spacecraft systems, and provide long-term timing references independent of any single nation or technology. The dream of autonomous navigation beyond Earth is also coming closer thanks to pulsar research. Spacecraft, far from global positioning system satellites and conventional navigation aids, can use the predictable flashes from X-ray pulsars to determine their position in space. This technique, known as X-ray pulsar-based navigation, or XNAV, leverages the sharp, regular pulses emitted by certain pulsars, which serve as cosmic signposts. X-rays offer unique advantages. They penetrate dust and gas, can be detected by compact instruments, and are less susceptible to interference than radio signals. The challenge lies in building detectors sensitive enough to catch the faint X-ray pulses from distant neutron stars, but progress is steady, and the first steps toward practical XNAV systems are already underway. Within this context, pulsar science is not just about looking outward. The precise timing of pulsar signals provides a stable reference that can be used to correct and update less stable onboard clocks, whether on satellites, remote observatories, or deep space probes. In some advanced concepts, pulsar-based timing could even synchronize networks of instruments on the lunar surface or throughout the solar system, creating a resilient, independent infrastructure for timekeeping and data transfer. The ripple effects extend even further. pulsars have become integral to the burgeoning field of gravitational wave astronomy. By monitoring the arrival times of pulses from an array of millisecond pulsars scattered across the sky, a setup known as a pulsar timing array, astronomers can search for minuscule deviations caused by passing gravitational waves. These subtle timing shifts might reveal the presence of merging supermassive black holes in distant galaxies or hint at more exotic phenomena, such as cosmic strings or phase transitions in the early universe. The precision required is extraordinary. Shifts of just a few billionths of a second can carry the fingerprints of events that occurred millions of light years away. The applications go beyond timing and navigation. Researchers are now exploring how pulsar signals might be used for secure time transfer, random number generation, and even space weather monitoring. The random quantum nature of some pulsar emissions could provide truly unpredictable numbers for encryption, while careful monitoring of pulse arrival times might reveal subtle changes in the interstellar medium, clues to the ever-shifting space weather between the stars. There is even speculation that pulsars could play a role in emerging fields such as quantum computing, though the details remain to be fully explored. Pulsar research has also left its mark on human culture and space exploration in unexpected ways. When the Voyager spacecraft were launched, each carried a map etched onto the golden record, showing the positions of cosmic radio sources, pulsars, relative to the Sun. These maps were intended as beacons for any distant finder, a cosmic address written in the universal language of pulsar periods and positions. In this sense, pulsars are not just tools for navigating the solar system, but also for communicating our place in the galaxy to any who might listen. As the pace of discovery accelerates and technological frontiers advance, pulsar astronomy continues to deliver surprises. New software and computational techniques are enabling astronomers to spot ever fainter candidates and confirm their nature more efficiently. High-frequency monitoring, once the domain of specialized teams, is now routine at many observatories, making it possible to catch transient events or subtle shifts in pulsar behavior that might otherwise go unnoticed. In the end, pulsars have become more than objects of scientific wonder. They are woven into the fabric of modern astrophysics, serving as both tools and teachers. Through them, humanity has learned to measure time and space with exquisite precision, to navigate the cosmos without reliance on terrestrial aids, and to probe fundamental questions about matter, gravity, and the universe's deepest mysteries. As new telescopes come online and new applications emerge, the hidden potential of these cosmic clocks continues to unfold, promising discoveries and technologies that will shape our understanding and exploration of the universe for decades to come.